In this lesson, we're learning how to use what is sometimes called the most important gas law. And this is one that pops up in lots of different chemistry courses. It's called the ideal gas law. And it's a fairly simple equation, but it helps us to solve lots of different gas problems. And this is the equation PV equals nRT. Now you may notice that this equation looks very different from the other equations that we learned in the last lesson. We don't have subscripts here. We don't have a P1 and a P2, for example. That means that in this gas law, we only have one set of conditions. We don't have, for example, like we had in Boyle's law, a starting pressure and a final pressure, or a starting volume and a final volume. We have just one set of conditions. PV equals nRT. We also have a couple variables that we didn't have in our previous examples either. Let's see what these variables stand for. Well, P stands for pressure. Now in this gas law, it's a little different from the others because pressure has to be in atmospheres. And if you're ever given a pressure that's not in atmospheres, then you're going to have to convert it to atmospheres. So for example, if you're given something in millimeters of mercury, you're going to have to use the fact that there are 760 millimeters of mercury in 1 atmosphere and do a conversion using that conversion factor. Pressure has to be in atmospheres. V, as you might have guessed, is for volume. And in this equation, volume has to be in liters. And once again, if you're given something that's not in liters, you have to convert it. So if you're given a volume in milliliters, you have to use the fact that there are 1,000 milliliters in 1 liter. Or if you're given something in cubic centimeters, which happens to be the same thing as a milliliter, you need to know that there are 1,000 cubic centimeters in 1 liter in order to solve that problem. N is a variable that we haven't had before. N represents the number of moles of gas. And so this represents the other property of gas that we didn't talk about before. In the earlier lesson, we said that all gases have 4 properties. They have a pressure, a volume, a temperature, and number of molecules. Well, this is where that comes in, number of moles of gas. And sometimes you're given not moles in the problem, but grams. And so you have to convert it to moles. We've learned how to do that in previous lessons, in previous chapters. And so you need to be able to convert from grams to moles again. We'll come back to R here in a second, but T is the temperature of the gas. And that's in kelvins, just like we've been using kelvins for several examples already. So in case you've forgotten, Celsius plus 273 is how you convert to kelvins. Now that leaves us with R. And R is a ratio. If you take any ideal gas, you can find the ratio between its pressure and volume divided by its moles times temperature, and you'll always get this ratio, which is sometimes abbreviated R. And that ratio is called the universal gas constant. And in chemistry, it's always the same number. It's always 0.0821. And it has units, as most constants do. It has some funny units, liter atmospheres per mole per Kelvin. Now, if you use the correct units, atmospheres and liters, moles and kelvins, then everything should work out correctly, and you should be able to use the 0.0821 without any problem. So let's try an example. Once again, all we have to do is plug and chug. So here's the equation, or the problem rather. It says a rigid steel container with a volume of 20.0 liters is filled with nitrogen gas to a final pressure of 200 atmospheres at 27 degrees Celsius. How many moles of nitrogen gas does the cylinder contain? So here we have a good example with the ideal gas law. We see it's the ideal gas law because the volume and pressure, temperature, nothing's changing. We just have one set of conditions. And it talks about moles, so that's a good sign that we need to use the ideal gas law. So P is for pressure, and the problem gives us a pressure of 200 atmospheres. So P will be 200. Now V is for volume, And it says the volume is 20.0 liters. And so volume will be 20.0 equals, now we have N. N is the number of moles. And that's what we don't know. The question says how many moles. So we're going to solve for N in this problem. R is the universal gas constant, which is 0.0821. So we're going to put that in for R. And T is for temperature in kelvins. Our temperature is given to us in Celsius, 27 degrees. So we have to convert that to kelvins to make that 300 kelvins. And so now all we have to do is solve for N, and we can multiply these by each other. We have on the left 200 times 20 is 4,000 equals N times, let's see, that's 24.63. So now we just divide both sides by 24.63, and it looks like N is 162. And in this equation, N is always measured in moles. That's the number of moles. And so even though I didn't carry out the units through the whole equation, some people like to put units in here, as long as I use the correct units, I can just remember at the end that N is in moles. Just like I remember that P has to be in atmospheres and T has to be in kelvins. Let's try one more example, a little bit more challenging. This time, it says what volume will 12.0 grams of oxygen gas, that's got a formula of O2, occupy at 25 degrees Celsius and a pressure of 0.520 atmospheres. So once again, it doesn't look like anything's changing. It talks about how much gas we have. So this sounds like the ideal gas law. So P is for pressure in atmospheres, and that's 0.520. So I'm going to plug that in here. Atmospheres. Now V is for volume, and we don't know what that is. It says what volume. So V is actually our unknown in this problem. Equals. Now N is for moles. But does the problem give us moles? It doesn't, does it? It just gives us 12.0 grams of oxygen gas. So before we go any further, we're going to have to take a little pause here, and we're going to have to convert from grams to moles. And so off to the side, I'm going to do that conversion. So I have 12.0 grams of O2, and I want to convert it to moles. So just like we've had in other conversions, the unit that we start with, grams, is going to need to go on the bottom, and moles is what we're converting to, so that goes on top. Now how many grams are in 1 mole of O2? Well, we have to look at the periodic table. And so here's the periodic table square for oxygen. It looks like oxygen has an atomic mass of very close to 16.00. But this is O2. So that means we have to multiply that by 2. So 1 mole is 32.00 grams. And so now we can take grams, cancel that out, and on our calculator, 12.0 times 1 divided by 32.00 gets us 0.375 moles of O2. So that's really a required step that we have to do before we can solve this problem. So I'm going to put in the 0.375 moles back into N. That's our N. Now R is next, and R is the gas constant of 0.0821, and T is the temperature in kelvins. Well, once again, the temperature is 25 degrees Celsius. So in kelvins, that's going to be 298 kelvins. And so once again, we have a math problem to solve. And so we have 0.520 times V equals, and the product of those three numbers is get my calculator. It turned itself off. 0.375 times 0.0821 times 298 is about 9.175. And now we divide both sides by 0.520 to solve for V. And the answer I'm getting is that it's about 17.6. And volume is measured in what unit in this problem? It is in liters. So that's the answer. So once again, we have a couple examples using the ideal gas law. It's a very fundamental gas law, but if you understand the math and understand the conversions that you might have to do, it's not that difficult.